right, so let's look at how this works with an actual function. So we're going to use the first derivative here to figure out our points of extrema and whether they are points of inflection, local mins, or local maxes. So I'm going to do this first one completely as an example, and then I'm going to try to give you one similar to do on your own. Okay? So listen carefully, hold your questions till the end, and then I'll take your questions after I do the full model if I haven't already explained it. Cool?
Yep.
All right, so for the first derivative, this is a pretty general function, a polynomial, so we're just using all the regular polynomial rules. So derivative of x to the third is going to be 3x squared, and the derivative of minus 12x is going to be minus 12, and then minus 5 gives us our plus c. So once we have our first derivative, we already know that we use our first derivative to find our points of extrema, so we're going to set that equal to 0. So 0 equals 3x squared minus 12. Bring my 12 over, bring my 3 over. So x is going to equal plus or minus 2. So these are my extrema points. So first, just like you've already done, just like you already know, we're going to plug that positive and negative 2 back into our original function so we can identify the actual points we're using on the graph. So when I do f of 2, that's going to give me 2 cubed minus 12 times 2 minus 5, 8, okay, 8 minus 24, negative 16, minus 5, we should be at negative 21.
Yeah.
Okay, f of negative 2 equals negative 2 cubed minus 12 times 2 minus 5 equals, so that's going to be negative 8.
12 times negative 2, right?
Yes, thank you. Negative 8 plus 24, that's going to be positive 16 minus 5, that's going to be 11.
Yeah.
So let's actually graph those points. So f of 2, and then we'll do 1, 2, 3, 4. I'll make each of these 5. And then negative 2, 11. So those are my 2 points, my 2 extrema points that are going to be either local mins, local maxes, or points of inflection. So now comes the part that the rule we just learned told us about. So I'm going to do a sign change analysis. So my 2 points where stuff happens, my 2 points where good stuff is going to occur are negative 2 and 2. So remember, I'm using my derivative. I'm using this 3x squared minus 12 plus c. So I'm just going to pick a point that's less than negative 2. You can do it abstractly. I like just to pick a point in the range. So I pick the easiest point I can that falls there. So I'm just going to use negative 3. So if I plugged negative 3 into this derivative, I would get 3 times negative 3 squared minus 12. So negative 3 squared is going to be 9, times 3 is 27, minus 12 is 15. 15 is a positive number. That tells me that every value that's less than negative 2 when I plug it in my derivative is going to be positive. Okay? So in the middle, well, this is easy. I can pick 0.
Negative.
So when I do 3 times 0 squared minus 12, that's going to be 0 minus 12. That's a negative 12. That means everything in this range is going to have a negative value for the derivative. So you can probably guess what's going to happen here. So let's plug in 3 squared. That's going to be positive 27 minus 12. That's positive 15. So again, this is positive. So now this is where we apply the rule that we just learned. We have a sign change in the derivative. So at negative 2, our sign goes from positive to negative. That means this is a local max. At positive 2, it goes from negative to positive. So that means that this is a local min. So now this is a graph of our original function. So this is the graph of our original function. We use the graph to give us back to the original function. Cool?
Yep.
All right. So try it with this function. Then we're gonna have to go back and I'm gonna have to give you some good nomenclature, but this way you'll have at least the math down, and then we'll get the nomenclature and then try it with one more where we do both. Good on the product roll. Let me see your product roll. Good. Good. So I'm gonna follow along with you guys up here since you are all that far. You don't even have to distribute the e to the x if you don't want. You can pull it out before you even distribute.
Oh, yeah.
This is her. Yeah.
I wrote Q for each one. Yeah, okay.
All right, so getting the points of extrema is just the first battle. Remember, you need to get to a point where I can see the graph. So show me your sign analysis. What about this?
Oh.
What happened? When is e to the x equal to 0?
When e to the 0 power is x, so it's 1.
Oh.
No.
Wait.
1 is e to the x equals to 0. Shukai just described when x is 0 what happens.
Oh.
That's different.
Oh,
This
that's
was
right.
not this. When is this true?
I'm just plugging off.
Never! Trick. This is never true, so you're right, ignore that.
Okay.
So
Oh.
this does not matter. We're just looking at these two as our extrema.
Oh, okay.
Okay?
So do we just write does not exist for e to the x?
Yeah. I mean, in this case, our goal is to get the graph, Shukai, so I think if you were trying to prove it, that would be a good element of your proof to say that you're ignoring that
Oh,
factor because it does not exist.
Okay.
Yeah,
So
Good. So let's see your picture. You need to have something on a graph. Good, Shikai. Great. Okay, so a little trick. So why did we eliminate e to the x when we were trying to identify points of extrema? Michael?
Because it's never equal to 0.
Correct. What else do we know about it? Not only is it never equal to 0, what else is true?
It's its own derivative.
Good. Yeah. It's always positive. So if this is always positive, I don't need to consider e to the x at all when I'm doing my sign change analysis. The only thing that's going to impact my sign are these two factors. So that's a little shortcut. This is always positive, so it doesn't matter. It's not going to change. Okay? So then what did you get for when x is less than -3?
Positive.
Positive. How about between -3 and 1?
Negative.
Greater than 1?
Positive.
Okay, when you plugged in x equals -3 to get your first extrema, what was the value of y?
0.299.
Good, thank you for rounding correctly. And when you plugged in 1, what was the y value? Spencer?
Negative 5.437.
All right, so graph, -3, I'll make each of these 1, no, like this, and then 1. So what does that tell you about this point? Is -3, when x equals -3, is that a maximum or a minimum, Shukai?
Local max.
Okay, how did you know?
Because the sign changed from positive to negative.
Correct. How about at 1, Spencer?
That's minimum.
Why, Michael?
Because it changed from negative to positive.
Excellent. So there's our function. So now, you guys just graphed a pretty complex function, or at least got an approximation of it using the derivative. Cool? So now we have to go back so that Mrs. Leishad allows me to live another day. And we're gonna make sure we get the correct nomenclature here, because that's gonna be incredibly important when you're taking the AP. When you're taking the AP, they're gonna wanna see you use the precise mathematical definitions for giving your answers. So what we said here, so we're using it to define the max and min, but if you go back to our definition, we want to be a little bit more precise than what it says. We're going to actually use the words increasing and decreasing, right? So rather than, so what happens is when this derivative is positive, what happens to the function is that the function is increasing, which you guys already know from your discussions about continuity. What happens when the derivative is negative is that the function is decreasing. Right, so we want to use that actual specific language here. So what we would say in our example problem is that the